All right, let's take a look at our Hardy-Weinberg problem set here. And, you might be wondering how this is useful. And just like a lot of things in the study of genetics, what's useful is the ability to make estimations and make predictions based on data. So this has to do with population genetics, which is also referred to as microevolution, and that's what we're studying in this unit. So one thing this would be useful for would be to show that there has been a change in the allele frequency or the frequency of genotypes in a population from one generation to the next. And to do that, we use this equation that's known as Hardy-Weinberg theorem, or the Hardy-Weinberg equation. So it's p squared plus 2pq plus q squared equals 1. So the equals 1 tells you that it's relative. And the P and the Q represent the frequency of alleles. So P represents the frequency of the dominant allele, and Q represents the frequency of the recessive allele in any population. Another thing that's important to note about the relationship between P and Q is that they are also relative. In other words, P plus Q also equals 1. Because they represent all the alleles for any particular gene in a gene pool. So, for example, in this case, we're looking at the gene for wings. So there's the allele, the dominant allele for wings, and the recessive allele for not having wings. And in the whole entire gene pool, there's the addition of both the dominant allele and the recessive allele adds up to 1. Or 100% of the alleles for that gene. So in this equation, the allele frequencies can be used to calculate the frequency of genotypes for any gene in any particular population. So for example, p squared represents the genotypic frequency of homozygous dominance. And q squared represents the genotypic frequency of homozygous recessives. And 2pq represents the genotypic frequency of heterozygotes in the population. And they all add up to 1. They're all relative to each other, and they add up to 100% of all the genotypes in the population for any particular gene. And I'll tell you right now, right off the bat, the one thing that you want to remember every time you're solving one of these problems is that you're going after the genotypic frequency of the recessive trait. And that's because that's the only phenotype that you know the genotype of. In other words, when you look at the both the p squared, in other words, the homozygous dominant individuals in the population, and the 2pq, the heterozygous individuals in the population, they both show the dominant trait. So you can't tell by looking at them whether they are homozygous dominant or heterozygous. The only ones that you know are homozygous recessive are the ones that show the recessive trait. So for example, in this population, by looking at these dragons with wings, you can't tell whether they're homozygous dominant or heterozygous, because either way they're going to show wings. The only ones that you know the genotype by looking at them, by looking at their phenotype, are the homozygous recessives. And that's the q squared term in this equation. Once you find the q squared term, then you can calculate not only the the recessive allele frequency, but then you can use that to calculate the dominant allele frequency, the p. And with that, then you have both p and q, and you can calculate the genotypic frequencies of the homozygous dominants and the heterozygotes from that. So if you don't understand what I just explained, don't worry about it. You'll probably catch on as we go through the example here. So in this example, like I said, you want to start by going after that q squared term. And so to do that, you need to calculate the phenotypic frequency of the recessive phenotype. The phenotypic frequency of the recessive phenotype. To do that, you count up the total number of individuals in the population, and in this example, there are 21. And then count up the total number of the recessive phenotypes in the population. So 1, 2, 3, 4, 5, 6, I missed one, 7. I think I missed that one. But anyway, there are 7. And to calculate Q squared, which again is the genotypic frequency of the homozygous recessives, that would be all these dragons that don't have wings, 7 divided by 21 is 0.33. And I circled that because that's one of our answers here. This is what we're being asked to calculate. So 0.33. Now from that, you can calculate Q. And remember, Q is the frequency of the recessive allele. And to get that, you simply take the square root of 0.33. Because 0.33 is Q squared, if you're going to find Q, then you need to take the square root of 0.33. And that ends up being 0.58. And that's our second answer. So Q, in other words, the frequency of the recessive allele, is 0.58. Once you have the frequency of the recessive allele, you can calculate the frequency of the dominant allele, in other words, P, by subtracting Q from 1. And again, Q is 0.58. So we subtract 0.58 from 1 because P and Q are relative. They always add up to 1. So we subtract 0.58 from 1 and we get 0.42. And that's our next answer. So that's the frequency of the dominant allele. Now, since we have the frequency of the dominant allele, we can calculate P squared. And again, P squared in the equation here is the frequency, the genotypic frequency of the homozygous dominants in the population. And that ends up being 0.42 squared. So that's what we calculated for P here. So we take P, 0.42 squared, and we get 0.18. Now, I like to express genotypic frequencies in percentages rather than decimals. So I didn't show it here, but you would multiply 0.18 by 100, and that would turn it into 18%. So genotypic frequencies and phenotypic frequencies I like to express as percentages. Allele frequencies I like to leave as decimals because that's what you're using to make calculations. So whenever you're doing calculations, you don't want to use percentages. You want to use decimals. So now that we have the allele frequency of both P and Q, we can not only calculate the genotypic frequency of the homozygous dominants, P squared, but we can also calculate the genotypic frequency of the heterozygotes. Remember, in the equation here, that's what 2pq represents, the genotypic frequency of the heterozygotes. So that's 2 times 0.42, which is the allele frequency of P, times 0.58, which is the allele frequency of Q, or the allele frequency of the recessive allele. So the dominant allele times the recessive allele times 2pq. And that ends up being 0.49. And again, that's a genotypic frequency, and so we want to multiply by 100 to make that 49%. And so those are all of our answers. So what's the frequency of the heterozygote dragons in your population, which is, again, 2pq? That's 49%. Now, the reason this was asked for twice as an answer is because that's what you're normally most interested in finding out in any population. In other words, how many of these dragons with wings are heterozygous? Because you can't see it, right? You can't see whether they're homozygous dominant or heterozygous. When you look at them, any dragon with wings can be either homozygous dominant or heterozygous. So if you want to find out how many of them are heterozygous versus homozygous dominant, then you can use the Hardy-Weinberg equation to find that out. Where would this become practical or important? Well, let's say, for example, you're trying to figure out how many individuals in a population may carry the allele for sickle cell anemia. So that would be an example of where you might want to use this Hardy-Weinberg theorem or Hardy-Weinberg equation to figure that out. That's the whole idea of population genetics. But again, you can also use this to show a change in the allele frequency over time, which is microevolution. So this is the dragon population at this time, but let's say these dragons reproduce and they produce another generation. how many, how do the allele frequencies change in that second generation? So you would make these calculations again for the second generation, and then compare those frequencies to the first generation. And if there's a change in the allele frequencies, then that represents microevolution. So you can see whether or not the population is at Hardy-Weinberg equilibrium. If the allele frequencies are changing from one generation to the next, then the population is not at Hardy-Weinberg equilibrium, and therefore it is evolving. And what I'm referring to as Hardy-Weinberg equilibrium, you also know as genetic equilibrium. So genetic equilibrium and Hardy-Weinberg equilibrium are the same thing, because Hardy and Weinberg are the ones that came up with the concept. So these problems are set up to start out relatively easy and then get harder as we go. So this one's pretty straightforward. If you understand what we did with problem 1, you should be able to figure out problem 2 here, because you're given what it is that you're looking for. What I told you, the very first thing that you should do is go after the genotypic frequency of the homozygous recessives. Well, here in this problem, they hand it to you. So you've sampled a population in which you know the percentage of the homozygous recessive genotype, and it's 36%. Using that 36%, calculate the following. So the first thing is the frequency of the homozygous recessive genotype, and that would be simply 36%. It's given. It's Q squared, right? And by the way, I would recommend that you write the equation on every problem, just to remind you of what you have to work with. And something else that you might want to add is the equation P plus Q equals 1, because all these frequencies are relative. So the allele frequencies are relative to each other. In other words, the frequency of the dominant allele plus the frequency of the recessive allele equals 1. Just like the frequency of the homozygous dominants plus the frequency of the heterozygotes plus the frequency of the homozygous recessives equal 1. All these frequencies are relative. So back to the problem. B here asks for the frequency of the recessive allele. And to get that, we simply take the square root of 0.36. So the genotypic frequency of the recessive homozygous recessive genotype is 36%, but if you're going to work with that, you need to turn it into a decimal. So don't take the square root of 36. You need to take the square root of 0.36, and that ends up being 0.6. Well, because the frequency of the recessive allele plus the frequency of the dominant allele equals 1, that means that once you have the frequency of the recessive allele, here is 0.6, you can calculate the frequency of the dominant allele simply by subtracting 0.6 from 1. And so here we have P. P is the frequency of the dominant allele. We calculate that by subtracting the frequency of the recessive allele, 0.6, from 1, and we get 0.4. 0.6 and 0.4 equal 1, right? They add up to 1. It's all relative. Part D here gets into more of what we would actually be looking for in calculating, because again, when you look at an individual that has the dominant phenotype, you can't tell whether they're homozygous dominant or heterozygous. All you can see is that they have the dominant trait. So these two calculations will give us the percentage of the individuals in a population that are either homozygous dominant or heterozygous. So homozygous dominant is represented by the P squared term in P squared plus 2PQ equals Q plus Q squared equals 1. So P squared is what we're after here. And we already have P, so P is 0.4, so 0.4 squared is 0.16. And we want to turn that into a percentage. At least I like to turn it into a percentage because I like to represent genotypic frequencies and phenotypic frequencies as percentages. So the genotypic frequency of the homozygous dominance is 16%. Likewise, we can just plug in P and Q into the 2PQ term of the equation. And P is 0.4, Q is 0.6, so it's 2 times 0.4 times 0.6, which is 0.48. And then we multiply by 100 and we get 48%. All right? So what we're dealing with in this example is a single gene trait, and it's completely dominant, which means we're only going to have two phenotypes. It's either going to be the dominant phenotype or the recessive phenotype. So here in Part E, we're being asked for the frequency of those two possible phenotypes. The dominant phenotype is a combination. It's the addition of the homozygous dominants plus the heterozygotes. They're all going to show the dominant phenotype. So that's 16% plus 48%, which is 64%. The recessive phenotype then is going to be what's left over, but it's also going to be what we calculated for the genotypic frequency of the homozygous recessives. The genotypic frequency of the homozygous recessives is equal to the phenotypic frequency of the recessive phenotype. So that's 36%. You can check that you did this right by adding because it's all relative, by adding the phenotypic frequency of the dominant trait to the phenotypic frequency of the recessive trait. And if they add up to 100, then you did it right. And it's the same for the genotypic frequencies. If you can add up the 3 genotypic frequencies, then you also, and it adds up to 100, then you also did it right. So it's a way to check your work. All right, this one's pretty easy too, because you're given the genotypic frequency of the recessive, the homozygous recessives. So the population is 100 students, and 4 students failed, and we're assuming here this is a single gene trait. And basically, the ability to do well in the course is controlled by a single gene trait and completely dominant. So 4% represents the genotypic frequency of the homozygous recessives. So we're asked for the frequency of the recessive allele. Well, if you've got the genotypic frequency of the homozygous recessives, it's simply a matter of taking the square root of that. But remember, when you take the square root of it, you need to turn it into a decimal. So in other words, divide by 100. So it's 0.04. Square root of 0.04 is 0.2. So there's our answer. That's the frequency of the recessive allele. Then we're asked for the frequency of the dominant allele. Well, remember that the addition of the recessive allele and the dominant allele adds up to 1. They're relative. They're relative frequencies. So P, which is the homozygous dominant, which represents not homozygous dominant, which represents the dominant allele, is calculated by simply subtracting the frequency of the recessive allele from 1, and we get 0.8. And those add up to 1, right? So there's your check. Then we're asked for the frequency of the heterozygous individuals, and since we now have both Q and P, we can simply plug that into the term. The 2PQ term is what this is asking for. Heterozygous individuals are represented by 2PQ. So 2PQ is 2 times 0.8 times 0.2, and that's 0.32. So in other words, 32%. And I hope we weren't asked for it, but I hope you can see that we could also easily calculate the genotypic frequency of the homozygous dominants here too. All right, we've got questions 4 and 5 on the same slide. We'll take them one at a time, of course. So within a population of butterflies, the color brown is dominant over the color white. 40% of the butterflies are white. So in other words, 40% of the butterflies are the recessive phenotype, right? That means that that's the same as the homozygous recessive genotype. So given this simple information, and they throw in here, and I didn't write these questions, by the way, which is something that is very likely to be on an exam. That is true, however. We want to calculate the following. And again, I put the equation on here just to remind you that all of these calculations are based on this Hardy-Weinberg equation, or Hardy-Weinberg theorem. So we're asked for the percentage of butterflies in the population that are heterozygous. Well, we're basically given that. All you have to do is take the square root of 0.4. But again, remember, not 40, not the square root of 40, the square root of 0.4, and that's 0.63. So Q is 0.63. P then is going to be Q 1 minus Q, or 1 minus 0.63, so it's 0.37. So 2PQ, which is what we're being asked for here, we're being asked for the heterozygous, the genotypic frequency of the heterozygotes, that's 2PQ from the equation. That's 2 times 0.37 times 0.63, or 0.47, or 47%. We want to multiply by 100 and turn that back into a percentage, because again, that's how I like to express both genotypic and phenotypic frequencies in these kind of problem sets. Then we're asked for the frequency of the homozygous dominant individuals, and that's simply p squared, which is 0.37 squared, which is 0.14, or times 100 to 14%. The check then is that the frequency of the heterozygotes plus the frequency of the homozygous dominants plus the frequency of the homozygous recessives should add up to 100%. So you'll notice that the heterozygotes plus the homozygous dominants here add up to 61%, and then if we add the 40% we were given, that actually goes over 100%. It's 101%, but that's all due to rounding and so forth. So it's close enough that the check checks out. All right, number 5 is a much more difficult question. You need to extract the necessary information out of the word problem here. So after graduation, you and 19 of your closest friends, so that's a total of 20 people, right? 10 male, 10 female. And since we're dealing with a single gene and complete dominance here, because we're dealing with cystic fibrosis, that's a total of 40 alleles. Each person, if you'll recall, in this population of 20, has 2 alleles for that gene. That's a total of 40 alleles. So that's an important piece of information, and that's an important way to look at this as you're reading this word problem. So we all charter a plane and go on a round-trip world tour, but the plane crashes on a desert island. Everybody survives, but no one finds them, and they start a new population, totally isolated from the rest of the world. So there's no gene flow, if you'll recall. That's what that suggests. So 2 of the friends carry the recessive allele for cystic fibrosis. In other words, both of them carry 1 recessive allele, right? So that means within this gene pool, for this gene of 40 alleles, 2 of those alleles are going to be the recessive alleles for cystic fibrosis. So assuming the frequency of this allele does not change as the population grows, in other words, 2 out of 40, what will be the incidence of cystic fibrosis on the island from generation to generation? And so it's not going to change. And I went ahead and wrote the answer here, but how do we get the answer? Well, Q, the frequency of the recessive allele in this case, is 2 divided by 40. There are only 2 alleles in the gene pool of 40 that are recessive. So that's an allele frequency of 0.05. Q squared then, which is what we're asked for the genotypic frequency of the homozygous recessives. So that's Q squared is 0.05 squared, and that's 0.0025. Well, then you want to turn that into a percentage by multiplying by 100, so that's 0.25%. And there's our answer. So this one's a little more complicated because you have to figure out what the information is, or you need to figure out what you need from the information given. So you want to remember that you're always trying to find the allele frequency of the recessive allele. So any way that you can do that, you need to do that from whatever information is given. All right, this one's pretty easy because it's very easy to see what you need or get what you need from what you're given. So cystic fibrosis is a recessive condition that affects about 1 in 2,500 babies in the Caucasian population of the United States. Please calculate the following. So the frequency of the recessive allele in the population, the answer is 0.02, but the way we get that is to take the Q squared term, because that's what we're after, the frequency of the genotypic frequency of the homozygous recessives, right? That's what we're always after at first. That's 1 divided by 2,500. 1 in 2,500 is given to you. So that's 0.0004. Q then is going to be the square root of 0.0004, which is 0.02. So there's our answer. That's the frequency of the homozygous recessives of the Caucasians in the United States. The frequency of the dominant allele then is going to be 0.98. It's simply 1 minus 0.02, right? Because P plus Q equals 1. They're relative to each other, so 0.98. And then the percentage of heterozygous individuals or carriers in the population is going to be 3.9, but we get that by multiplying P and Q and times 2. So 2 times 0.98 times 0.02 is 0.039, or multiplied by 100, it's 3.9%. All right, so that one's much more straightforward than what number 5 was. But again, getting back to the purpose of all of this, that piece of information right there, knowing that 3.9% of people in the population are carriers of cystic fibrosis, is important in trying to find out, how the disease is being passed from parents to offspring and generation to generation in the population. You might be able to figure out from generation to generation whether it's increasing or decreasing, and hopefully it would be decreasing. All right, in this case, the only thing that makes this tricky is we're dealing with incomplete dominance, but don't let that throw you. A single gene locus here refers to the fact that this is a single gene trait with 2 alleles, but incompletely dominant. And this is supposedly real data. So 1,612 individuals, 1,612 individuals, 1,469 are homozygous dominant, 138 are heterozygous, and 5 are homozygous recessives. And because this is incomplete dominance, we can actually see that from the phenotype. In other words, these are phenotypic. These are the numbers of these 3 different phenotypes in the population. So we're simply being asked for the allele frequencies here, the frequency of the dominant allele and the frequency of the recessive allele. But we always start with the recessive allele. Even if you have information for the dominant allele, you always start with the recessive allele. Just by convention, that's what I highly recommend you do. So Q squared is 5 divided by 1612, so it's 0.003. Q then is the square root of 0.003, which is 0.056. So that's our answer for Q. That's our answer for the frequency of the recessive allele. Then we simply calculate the frequency of the dominant allele by subtracting Q from 1. So it's 0.056 from 1. That gives us 0.944. So that's the frequency of the dominant allele. And we're done. That's all we were asked for. However, of course, we could use these to calculate anything we wanted to in terms of the genotypic and, in this case, phenotypic frequencies in the population. Genotypic and phenotypic frequencies would be one and the same because this is incompletely dominant. All right, we're finally to the last 2 problems, and so in number 8 here, the allele for widow's peak, which is a trait that we've looked at before in our notes. If you'll recall, it's a dominant trait, so having a widow's peak is dominant over not having a widow's peak. So it's dominant over the allele for straight hair in a population. Straight hairline, I'm sorry. So in a population of 500, we've got 25% that are recessive. And that's the information you need right there. 25% are recessive. How many individuals would you expect to be homozygous dominant and heterozygous for the trait? And again, this is primarily, what you'd be most interested in, to see how that trait is being inherited and passed from generation to generation, and how it's changing in its frequency from generation to generation. So Q squared is 0.25. I mean, you can just go ahead and write that out. Just change the 25% to a decimal. Q then would be the square root of 0.25, or 0.5. P would be 0.5 subtracted from 1. 1 minus 0.5, so it's 0.5. So in this case, Q and P are both 0.5. The frequency of the homozygous dominance then would be P squared, right? That's the term in the equation. P squared is the frequency of homozygous dominance. So it's 0.5 squared, that's 0.25, times 500 is 125. So this is the only thing that makes this problem different. We're being asked for how many individuals. We're being asked to calculate out of a population of 500 how many individuals would be expected to be homozygous dominant and heterozygous. So whatever the genotypic frequency is, you simply multiply that by 500, the total number of individuals in the population, to get the number of individuals that have that genotypic that have that genotype. So 125 are going to be homozygous dominant. Same thing for heterozygotes. It's 2 times 0.5 times 0.5 times 500 the number of individuals in the population, and that gives us 250. Now, we're not asked for the homozygous recessives, how many homozygous recessives there would be, but I'm sure you can see that from the numbers we have here out of 500. It would be 125. So we're dealing with here, because the allele frequencies are both 0.5 for both the dominant allele and the recessive allele, we end up with what you would predict from a Punnett square in this situation, a 1 to 2 to 1 genotypic ratio and a 3 to 1 phenotypic ratio. All right, this next question, or the last question, has to do with hitchhiker's thumb, and I just wanted to show you what hitchhiker's thumb is. It's the ability to bend your thumb backwards. And some people can do this and some people can't, but that's what question 9 is asking about. And of course, it's genetically controlled and it's a single gene trait. So the allele for hitchhiker's thumb is recessive compared to straight thumbs. In a population of 1,000 individuals, 510 show the dominant phenotype. How many individuals, so again, here we're asked for the number of individuals, how many individuals would you expect for each of the 3 possible genotypes for this trait? So from the information provided, a population of 1,000 individuals, 510 show the dominant phenotype, so that's 510 divided by 1,000. So the frequency of the dominant phenotype is 0.51 or 51%. But we're going to leave it as a decimal because we're going to use it for further calculation. So this really doesn't tell you anything, because these dominant individuals can either be heterozygous or homozygous dominant. But we can use that to figure out the frequency of the recessive trait. In other words, the recessive phenotypes. In other words, the number of individuals, or the frequency of the individuals that have hitchhiker's thumb. And that's simply by subtracting 0.51 from 1, because the phenotypic frequency and the phenotypic frequencies are relative, just like the genotypic frequencies and just like the allele frequencies. Everything's relative. So 1 minus 0.51 is 0.49. 0.49 of 1,000 people is 490. So right there we have the number of individuals that can be expected to have hitchhiker's thumb. We can go on then to find out Q and P. So Q squared in this situation is 49%. So that's the frequency of the homozygous recessives. That means the frequency of the recessive allele is the square root of 0.49, which is 0.7. P then is going to be 1 minus 0.7, which is 0.3. We can then use the P and Q there to calculate everything else that we need. So 490 are the number of individuals in this population that are recessive, homozygous recessive, but we also are asked for how many individuals are going to be homozygous dominant. So that's P squared, which is 0.3 squared, and that's 0.09. 0.09 times 1,000, or the way I like to read this is 0.09, or 9% of 1,000 is 90. And then 2PQ would be the number of individuals, will allow us to calculate the number of individuals that are heterozygous. So 2PQ is 2 times 0.3 times 0.7, which is 0.42. 0.42 of 1,000, or 42% of 1,000, is 420. And there we have the number of individuals of each genotype in this population of 1,000. So again, Hardy-Weinberg theorem, or the Hardy-Weinberg equation, is very useful if you're trying to figure out how populations are changing over time from generation to generation.